So we have two things that we got from last chapter, which was the work energy theorem. So this is going to be conservation of energy. Of mechanical energy. So from last chapter, we had work is equal to the change in kinetic energy. Also, we know that work is equal to the negative of the change of potential energy. If two things are equal to a third, they're equal to one another. So change in kinetic energy is equal to the negative of the change in potential energy. And honestly, that's it. It's just that simple. That's the first equation for conservation of energy. But it's not the most practical equation, not the one that we'll be using to solve problems, starting from that point of view. So let me do some mathematical manipulation. This is energy conservation. Let's get a couple more forms of this. K final, delta K is K final minus K initial. Minus delta U, which is U final, minus U initial. We'll translate the minus sign through on the right side. So over here, we still have K final minus K initial. Over here, we have K initial minus, so U initial minus U final. Now I'm going to get all the final and initial stuff on the same side. So K final, and then I'll take a minus U final over on the other side. And that equals, if I bring the K initial over, I have K. All right, so that's plus. When I take the minus over, it's plus. And minus K on the other side is plus Ki, and then plus Ui. Now I want to define something called mechanical energy. I think I've said it before, but we haven't written it down as a mathematical equation. So there are several types of energy in physics. You know, there's heat energy, which is not considered mechanical, but it actually comes from mechanical. It's the conversion of mechanical energy into a different type. If I take kinetic energy, right, and rub my hands together, so that's kinetic because my hands are moving, you know, your hands heat up. Well, the frictional force between the surface of my hands is converting some of that kinetic energy to mechanical, and then it dissipates and leaves the system because it's going to heat up the air around it, the molecules, whatever, but that's coming from the work done by my hands on one another. So heat energy is a type of energy, but it's not mechanical. Then we have sound energy. I've demonstrated that before, that again, sound energy can be converted to three types when you have something like a mass fall into the ground. Actually, this is a really good example of, I've done it before, I'll do it again. So right now, there's no energy, no mechanical energy on the object if you assume the top of the plate is zero, is the origin. So the gravitational energy is zero because it's there. I'm going to do work on the object and pick it up. How much work do I do? mgh. Well, more than that because some of it is lost to friction because I'm touching it, but it has mgh. So now that energy came out of me from my biological processing my food and exerting energy and force on the object. Now, when I drop it, that we'll see that and show how that potential energy is converted to kinetic. So that's transferred. Now that's, you know, if you don't assume drag, then that's conserved. But then when it hits the ground, the energy leaves the box in three ways. makes a sound. So there's sound energy. That's a class of energy itself. There is, you can see it in some of these shows where they, I went to see Black Adam last night, actually. And there's one point where he claps his hand and it sends off a concussion wave and a pressure wave, and it knocks people down. Well, that's energy. Energy is in sound. And you can make all kinds of sonar devices that can be weaponized, actually. Anyway, energy. But also it hit the table. So there's a little bit of friction there. It heats up the table a little bit. But then it sends a wave, a mechanical wave out through the material that dissipates. Just like, I always say, if you were Whoville living in a valley in this on this board, it would feel like you had an earthquake. Because that's really what an earthquake is. It's in ripples, spherical waves, circular waves anyway, through the earth. So, and waves have energy, as you can see from tsunamis and earthquakes. So all of those three forms of energy are not really considered mechanical. Wave energy isn't really considered, it's wave energy. You might call it mechanical if it's in something like a solid, like a rope. You could it's a form of mechanical energy, but it's not, it can be described in a different way than what we're doing here, but it is comprised of potential and kinetic of the energy of the medium. So but that's not what we're talking about here. Nothing's waving. And of course, sound. So sound, heat from friction, and then mechanical wave energy. So in general, energy is always conserved, but when we're talking about conserving energy and not conserving energy in these systems, ouch, we're specifically referring to mechanical energy, whether it's conserved, stays in the system or not. So we need to define what mechanical energy is. And it is essentially the kinetic energy plus the potential energy of the system. So that comprises the total mechanical energy of the system at any given time or any given point. So we define it right now. Mechanical energy is, the symbol we use is E. It's a scalar quantity as well. And it is defined as kinetic plus potential. That's it. So this is mechanical energy. Now, I'm going to substitute equation 7 into equation 6 and write it a little bit differently. Now that I have the mechanical energy there, you can see that the left side is K plus U final. So that would be final kinetic energy equals Ki plus Ui. So that's initial kinetic energy. So there you have the second form of conservation of energy. It says that between 2 points or 2 different times, the total mechanical energy of the system equals what it was at some final time or final position. This is the form of conservation of energy that is kind of the most practical, that we'll be using a great deal in problems that we do momentarily. Essentially when mechanical energy is truly conserved. Now, we spent a lot of time talking about conservative forces last chapter, and I did that. I think they do it in this chapter for you. So by the way, we're really ahead because all of that stuff like conservative, non-conservative forces, and many of the potential energy functions and you know, the spring, all that, that's actually done in your book. It's done in this chapter on conservation. I guess that would be chapter 8. But I like to put it in chapter 7 of my notes. So we've already discussed it. So we basically already done half the chapter of 8. So you can go ahead and read through that stuff in the examples though. So we really only have 2 sections: conservation of energy truly, and then how to do conservation of energy whenever mechanical energy is not conserved. How do you handle it? So that's the last couple of sections of the chapter. So this is the third way to do it, but there is the second way. This is a fourth way that I like, which is we don't really need it when energy is truly conserved, but we will kind of, it's nice to have it as a reference for when we get to when energy is not conserved. So what I was about to say is that you're going to know in a system whether the mechanical energy is going to be conserved or not, even before it does anything, because based on the way the situation is set up, only conservative forces do work. If only conservative forces are doing work on a system, that means that the mechanical energy will be conserved. So you can evaluate that actually even before you kind of do a thought experiment of the problem or run through the system, you can see it. So I would suggest using this version whenever there is only conservative forces are doing work on the system. When non-conservative forces are also doing work on the system, then we have to derive something called a modified work energy theorem. But if I just subtract these 2 things, right, the delta quantity, E final minus E initial equals 0, or delta E equals 0, that's another way to write conservation of energy. And that's a really useful thing to at least recognize mentally, because, or acknowledge, because when we derive the modified work energy theorem, we can relate it to this and talk about what the difference is and why we should use the modified work energy theorem in that form, why I like to use it in that form. And that's it, folks. There's no other theory. Basically, yeah, that's it. What we should do now is just start doing problems. I have several problems that we can work through. A lot of them are problems that we've worked through with other means. In fact, let's start with that. When we did work, one of the first problems I gave you was a problem where we had a block sliding down a plane at angle theta. Well, we did that also with forces, and we did it with work, and we compared the answer, the final velocity, to what we did with forces. Now I want to go back and take a look at that result, because now we're going to do the same one, but instead of using work energy theorem, which is what we did the last time we did it, I want to do conservation of energy to show you how to do conservation of energy. So remember what is given here. There's only 2 things. I think we had 3 things. We had M. I also gave you delta X. I told you that distance delta X was the total top, the horizontal distance, well, the distance along the plane. So what's given? So given M, theta, and delta X, use conservation of energy, namely equation 8, to find, let's call it V2. If V1 equals V0 equals 0. So 1 and 2. Well, one of the ways that I like to do conservation of energy is you set up a before and after, position 1 and position 2, or whatever, something like that. Because the thing about conservation of energy is that you're only concerned with what's happening, only concerned with 2 points. You're not really concerned with what happens between those 2 points. which wasn't necessarily the case for using forces or work energy. So the 2 points that I'm going to establish are the points where the object ends and begins. So the initial point I just call, V1. I like to use 1 and 2 as opposed to numbers as opposed to initial and final. So that's initial position 1, and it starts from rest. So I said that V1 equals 0, and down here V2 is the that's the final position there. Okay. So what you want to do is set up a conservation of energy between those 2 points. So that's why you see this equation is fun. So the next step then is to just apply conservation of energy. So applying conservation energy, I want to know the initial energy at position 1. That's got to be equal to the energy at position 2, mechanical energy at position 2. Mechanical energy is kinetic plus potential. So you have U, and 1 plus K1 equals U2 plus K2. I'll go one step further, I guess. So we know that in general, that's why I derive the potential energy functions. For gravity, the potential energy function is just mgh. So I have mg, I'll call it y, mgy1 plus, and kinetic energy is always 1/2 mv1 squared, and that's got to be equal to mgy2 plus 1/2 mv2 squared. Now, we can go ahead and I didn't establish an origin, but we always kind of want to do that, at least be set up to evaluate forces and things if we need to. But energy is a scalar function, so that makes things easier for us in a lot of ways. But still, I like to go ahead and set up a coordinate axis. And the easiest thing here is I've just got 2 positions, 1 and 2, so we don't really have to put the thing on a plane. I mean, we're energy is measured relative to the ground, and we don't really have to evaluate forces. It's useful to do that, but we don't. Anyway. So, yeah. So now evaluate the. You know what? I'll let you finish it out. See if you can do that. But go ahead and from equation 13, evaluate the zeros. For example, the initial kinetic energy starts from. And when it gets down to the final position 2 here, the y is going to be 0, so potential energy is going to be 0. So go ahead and see if you can finish that, do that problem, and do that problem and compare it to the answers we got when we did the work energy theorem and when we did forces. You see, we've only done 3 steps, and we didn't have to do it that many because I just wanted to be clear to you. You could have done this in 1 or 2 steps. So go ahead and do that. Do that right now. Yeah. Good, knock it out because I want to give you some other problems. Anyone get a solution though? What'd you get? Dominic, did you get a solution? Sounds working. Theodore, you did? David.
No, I'm trying, but like for some reason I think it's because I didn't sleep very well. I can't even really figure out how to start. So my apologies.
All right, no worries. Armand. So first, to start by getting the zeros out. Which terms are zero? David.
E.
E.
Wait, sorry.
Equation
No, it's
13.
because
All
I
right,
was looking at sorry, I was looking at equation 9. Sorry
gotcha.
about
I'll
that.
let you. I get it. I'll let you wake up. Armand. Yeah.
Is the final potential energy as well as the initial kinetic energy zero?
Yeah. So that term, because V1 is zero, so that guy is zero. The whole thing is zero. And this guy is zero because Y2 is zero. Yeah. So that reduces to probably something you saw in high school. This whole equation. You've probably done something like this in high school. We're just dropping it or whatever. Anyway, you get mg y1 equals 1/2 mv2 squared. Now, you got to be careful because in this equation, again, equation 6, what are the unknowns? Well, I'm looking for v2, but y1 is actually also an unknown. I don't know that. That's actually this distance over here. It's the distance that I am from the, along the vertical. That distance actually is, well, that's position. I'll call it position y1 along my, or y initial, I guess you could say. I don't know that distance, but I have geometry. I know the angle, so I can figure it out. I mean, I guess you would call that length h or something. In fact, let's say y1 is position, and basically this height is y0, which is 0, but I'll call it y0. Let's call it h. Sure, why not h? So y1 minus y0 is equal to the height h. I don't know that, but by geometry, so basically you can see since I have two unknowns, if I solve for y, if I can find y1, then I can put that back in and get v2. So, or by other techniques, problem solving techniques that I've taught you, I've only applied one concept, I've got one equation, but if I have two unknowns, I at least need another equation coming from the same concept in some way or another concept. Turns out this concept is not a physics concept, it's geometrical or trigonometrical. It's the Pythagorean theorem thing, not the right triangle thing. So that's theta, and that's delta x. That h is equal to delta x times the sine of theta. So I get it from there, right? So I plug that into equation 14 and then solve for v, and I'm done. So m delta x sine theta is equal to 1/2 mv squared. So see if you can finish from there. Just do the algebra to solve for V, and then check that, or V2, and check that with the solution we got last week when we did it with work energy. And also we had checked both of those solutions with what we did when we did mechanical, when we did forces, because we did that problem back, with Newton's laws applied to the blocks on the plane, and see that it comes out the right. But this is, for me, by far easier than both of those other methods, right? It's just, so it shows you the power of conservation energy. Now, you can't figure out the acceleration or anything like that directly from, but you can get the velocity very quickly. Well, that's cool. Nice. And they're completely different theories, it's really interesting to see the symmetry of physics, how it works out like that. So go ahead and get that final solution. Oh, then we're going to do several other problems. Yeah, so if we finish this out, first of all, the masses cancel out. That M cancels that M. Multiply the two across and take the square root. And our final result is V2 is equal to the square root of, it's going to be 2g delta x sine theta. Compare that to last week, you see that that was the solution we got. Does that make sense, everybody?
Yeah, that makes sense.
Okay. Let's do some more. Yeah, so there's um vision problem. Let's make up some here. conservation of momentum for that, don't I? Next chapter. All right, let's just keep it rolling. Let's just guess I could go ahead and put in modified work energy, but I want to do a couple more before that. Let's do I don't know why I'm drawing a blank. What did I do before? I did there's a problem in your book. Actually, I'm gonna have you look at it. Let's choose some from the book. That's probably a good thing. Do some intermediate problems in the book. For some reason, all the ones I was thinking about involved momentum. That's next chapter. We have to haven't talked about conservation momentum yet. So let's just get so course resources. Chapter 8. Let's just go to the end of the chapter and do. Yeah, problems, questions. Okay. That's also a pretty good one. So let's do, sure, we could do something like that. That's a nice one too. Loop to loop. Okay, we can do that. Still got you. All right, I'm gonna do there's an angle change. Yeah, as you can force and drag. I want to do something else. So with that, with modified work energy. Yeah, that's a cool one. We don't have to do on the spring. Compress attention is what is. Yeah, I'll do something like that. We'll do that one. Let's do it. So I jog my memory. Okay. um all right, so I know how to proceed. So let's I'm gonna go ahead and put in friction now. I'm gonna go ahead and do that. So we have that at our disposal. And we can do a lot more problems, including the ones we just looked at with friction. And it gives me an opportunity to make a distinction between what we're talking about. So what if we have friction on this surface? We've done that problem as well, right? And we know that, you know that if I add friction here, then the velocity at the end should be less, right? Because friction is, oh, you can't see it, sorry. Both cameras. Yeah. So what if I have friction here on this surface? You would imagine, well, Adrian, is Adrian there? Oh, he must have left. So David, I put friction here. Do you think the velocity when it gets down to the bottom will be greater, less than, or equal to what we just derived? And why?
At the bottom, if the mass moves from the top to the bottom, would it be greater than the velocity we just found?
If you add friction, you think it's going to be greater?
Yes.
Okay.
Yeah, I'll say
Anybody
yeah.
want to?
I'll say yeah. Let's stick to it. I'm
Okay.
gonna say yeah.
Okay. So somebody want to comment on that? What does friction do in terms of interacting with the object? Armand?
It essentially slows it down and makes it much more, well, it makes it much more, I think, costly in terms of energy to get down the entire ramp.
Why? What do you mean by costly, and why would it be slower?
Well, friction requires an object to put in. I don't know how to exactly phrase this, since it sort of sounds like I'm not sure what the word was, anthropomorphic. No, it requires the object to give a bit more energy to overcome it and keep continuing down its path. It'll be slower because it's going to be hitting friction at every point on the ramp and having to overcome it every single time. It's going to slow it down. It's going to lose energy as a result. So at the end, it will end up being slower with less energy.
Yeah, basically you said that well. You could do it more efficiently. One way you could say is that friction is going to do work on the system. And we know that friction does negative work, not positive work. So David or anybody, what does negative work mean? I told you about it, what it means. Will you tell me? What does it mean to do negative work versus positive work? Go ahead, Armand. That's, you're just talking, right? Who's just
Yeah.
talking? Yeah. It's basically what you said. Like negative work takes energy out of the system. It converts the mechanical energy to heat. So it'll have less mechanical energy when it gets down to the bottom. And so whereas in the case of the frictionless, all of the potential energy was converted to kinetic. That's what this equation is saying right here. But when friction is there, some of that mechanical energy will be converted to heat. So we're going to have less mechanical energy when we get down to the bottom to have been converted into kinetic energy. So it'll slow it down. Wow. Now, the book teaches you how to deal with that in a specific way, but I'm going to teach you a different way. I'm going to basically derive an equation that looks like this, but over on the right side, when we take the difference of the mechanical energy, it's not going to be equal to zero. It's going to be equal to something else, basically the work done by friction. So in that form, I like that form better because it clearly shows that the left side is the change in mechanical energy, and the right side is how much mechanical energy left the system and was converted to heat. And so it's called the modified work energy theorem. So I'm going to come over here and I'm going to derive that for you right now, and then we'll have that. That'll basically be all the theory we need for the whole chapter, and we can just go back and work various problems with friction forces, non-friction forces, or whatever. So that's kind of what I was struggling with, because I want to kind of mix some problems with friction and non-friction. And so I need to go ahead and put that in the way that I want. So let's start over here. The way to do this is you start with the work energy theorem. Now I have to tell you a little bit of something about that I didn't say before, because I wanted to go in stages. So over here, the work equation 1 is the work energy theorem, and equation 2 is the general definition of potential energy. Now let's go back and think about these equations a little bit more. With this equation here, I didn't really make a distinction between conservative and non-conservative forces. As it turns out, this equation encompasses both conservative and non-conservative. It applies to both conservative and non-conservative forces. In other words, I could define a total work on the system, work total is equal to work done by conservative forces, which I write work sub con, plus work done by non-conservative forces like friction. So even though it did apply here, I didn't emphasize it, I want to rewrite this equation and emphasize that it's the total work by both conservative and non-conservative forces that's equal to the change in kinetic energy of the system, okay? So we can write the work energy theorem, as a work total equals the change in kinetic energy, whereas the understanding that the total work is equal to work con plus work initial. Or maybe I should just go back and do that over here so I don't break my rhythm over here in my derivation. I just do it there. Yeah. Now,
Professor, I can't see the very right side of the board.
oh,
Yeah, there you
is
go.
that now?
Yeah.
So work total is equal to work done by conservative forces plus work done by non-conservative forces. And I'll just change this here. Now, let's consider equation 2. I'm going to ask you a question, kind of a little quiz, verbal quiz question. Can I do this when I talk about the work of equation 2 here? Is that going to be the total? Can I replace that with total work like I've done here, where total work equals work done by conservative forces and non-conservative forces? Can I do that with that work as well? And explain your answer. Why or why not? Anyone? Malachi, how you doing today? You came in. You came in a little bit late. I don't want to let you catch up. You feel like you want to give that a shot? I think we did talk about that last week though, but implied it, didn't say it directly. Are you there, Malachi?
Yeah, I'm here, but I'll actually pass.
Okay, no worries. Theodore, how you doing?
All right.
You there? Yeah, can you? What about that? Can we say that work is both conservative and non-conservative as well? And why or not? Why not?
I want to say work is not conservative. Mostly because, like, it's still, like, it requires energy to be put into it for it to actually, like, happen. And that's requires, like, in its own sense of it, like, it still requires, like, I guess, well, work or energy. I'm probably saying it, like, weirdly.
Well, let me help you a little bit. Conservative work will be done by conservative forces, and non-conservative work will be done by non-conservative forces. So what I'm really asking in equation 2, is there some way, by the way that equation is written, that you can tell with, and not knowing anything else, that you know that the work is done by either only conservative forces or by only non-conservative forces, or both non-conservative and conservative forces? That's my question. And you said non-conservative, but you didn't really base it in. So I want you to talk about forces, the types of forces that would contribute to the work that would give rise to an equation like that. That's the first hint. I don't know if that's helpful or not. Anyone else? David? Yeah.
I would say you would not be able to do the same thing. Or sorry, that doesn't make sense. I'm gonna say that you can't say that work is equal to work total because it's potential energy, which means that no forces are being acted or no forces are being done yet. That makes sense. I don't know.
No forces at all?
Well, I mean, I'm seeing potential energy as, like holding my phone 5 feet above the ground and just holding it there. No work is being done. Well, I mean, I guess my fingers holding the phone, but specifically in the phone, like I'm not dropping it, or it's not like friction is acting upon it. That's just my logic that I'm using to try to say that. That's why we cannot say that this is equal to work total, because no forces are being acted upon on my phone.
Okay, if you're just saying it has potential energy at that point,
Yeah,
but
that's
that
what I'm saying.
but okay, with that logic though, then that equation doesn't even make any sense, because we're saying, and it's not, and by the way, it's not just the potential energy at a particular point, it's the change in potential energy. That's what that's equal to. That's what the delta
Oh,
E
okay.
means.
All right, yeah.
So yeah, so like, remember where we got that from is when we were looking at, like force of gravity on an object and things like that, you know.
Okay.
So it's between 2 points. So to get it from the ground to your finger, let's give a different hint in the context of that thing you just said, that example you just gave. We defined conservative and non-conservative forces. David, can you remember what the definition of a conservative force is? There were 3 points. It was defined by 3 criteria. What were they?
See, sorry.
Sorry, you can look back at your notes.
Yeah, I'm trying to find them. It's from moving something from one point to another.
Okay, yeah, but go ahead. Give me the list of the 3 criteria. What about it?
Gravitational force, spring force, and electrostatic force.
Those are the examples. I'm asking you, how do you know that they are conservative? What is the criteria that makes them conservative? So yes, those are conservative forces.
I don't know. I sorry.
Okay. Well, you got us halfway. Anybody else want to chime in? What are the 3 criteria that determines that a force is conservative?
The work equaling 0 through a round trip, the work being done
Awesome.
done independent of a path, and being a potential energy function.
Yes, or having a potential energy function. That is right. And so keep going, Theodore. What are non-conservative forces?
Non-conservative. I think I forgot to write that one down.
It's just the opposite. You do know. It's just the opposite of all those, the negative of all those points you made.
Oh, okay. Well, in that case, then it would having work through a round trip, having its work be a part of a path, and not having potential energy function.
Well, work being not part of, but like dependent upon the path that it goes on. So different work for different path, even between the same 2 points. That's how you would say that.
Okay.
Yeah. And the thing that is significant to this answer is, what's the last one you said, David or Theodore?
Having not have a potential energy function.
Yeah, they don't have potential energy functions. And we illustrated that when we looked at friction. We showed how when you do friction, between any path, it doesn't give you a function, it just gives you a number. That number being the amount of heat that is dissipated. Like you don't get like a y or x in that final solution of the analytical solution like you do with gravity. Like gravity, the potential energy, the work done was mgy, which was h. Then we gave it a value h, and then with the spring it was 1/2 kx squared. When we did friction, we just got a bunch of constants in there, constants associated with the system, like the radius and so that's just a number, it's not a function. So just by looking at equation 2, and I did say it when I derived that equation, I wrote it down for you, that it only applies to conservative forces. I did say that, but I didn't do what I'm about to do now. I want to emphasize it by saying that since non-conservative forces don't have potential energy functions, you can't even apply this to them. That this is the change in the potential energy, which is the change in the potential energy function. So it could only possibly apply to conservative forces, the work done by conservative forces. So I'm going to put that in as an to emphasize now that we want to make a distinction between the types of work that's done with those equations. So that was always true. It's just that I didn't emphasize it because I didn't want to confuse you, because we didn't need it for what stuff that we were studying that I was talking about then. Now we do need it. We need to make that distinction always, okay? So I can now combine equations 1 and 2, actually, now that I'm making that distinction. That this basically is equation 1. Well, not quite, let me put it in. So let me rewrite it like equation 1 like this. If I take 19 and put it into 1, this is what I have. I have that work con plus work non equals delta K. But now, from equation 2, I see that work con is equal to negative delta U. So I can take equation 2 and put it into equation 19 right here. So what I'm going to have is negative delta U plus work non equals delta K. Okay. Now I'm going to take the negative delta U on the other side. And now what I have is work non equals delta K plus delta U. Now, I can leave it like that, but that's a bit messy. I like to clean it up a little bit, make a bit more efficient equation. So we'll do something similar with what we just did a few moments ago. I can, I'll leave the left side alone for a minute. And over here, we're gonna have K final minus K initial, and then plus U final minus U initial. We just expand the delta quantity. They put final and initial stuff together. So work non, and that's going to be equal to K final. We'll put that together with U final. And then we have a minus K initial and a minus U initial. I can factor out the minus sign and just say minus quantity K initial plus U initial. Now I'm going to use this definition of mechanical energy in equation 23. So that gives me that work non equals E final minus E initial. Now I'm going to define that as a delta quantity, and let me kind of flip it around just to compare it better. So I'm going to have, so E final minus E initial is delta E. Delta E equals work non. And now I'm going to use the definition of work, where I'm only talking about the work due to conservative or non-conservative forces like friction or drag. It's the only ones that we have thus far. It's the only one you have to think about. So basically, I have that the change in the mechanical energy is equal to the integral of the non-conservative force, friction or drag, dotted into dx, because that's the definition of work. So that thing right there, basically 25 and 26. 25 is a more concise version. Let's just, but that just reminds you how you need to calculate the work done by the non-conservative force. So if you compare equation 25 to equation 10, now you see what I mean. I would encourage you to, whenever, so when you get into a problem and you know that there's an object that has, where the only work being done is by conservative forces, then you know mechanical energy is going to be conserved, and you do use that equation, equation 10. If you see that non-conservative forces are doing work on the system, don't even start with this. Start with this thing here. That's called the modified work energy theorem. Because what it's showing you is that between two positions, the change in mechanical energy is not equal to 0, meaning energy comes out of the system. So when this block, when I put friction in, when this block goes from position 1 to position 2, in the inter time, friction is doing work on it, like we said, take energy out. How much of it? Well, it's going to be equal to all the stuff on the right side. So you can figure out, calculate the work done by the friction as it slides down, which we actually have done. And then that's just equal to the change in the mechanical energy. So that sets up an equation where you can solve for stuff in the interim that, you know, quantities that are associated with that you don't know. So the book is not going to teach you that. I don't think they have the modified work energy. They teach you to do it another way, which is, I think it's kind of confusing. It's confusing for me. Basically, you kind of say start with conservation energy, then somewhere in there show the amount of work that was taken out. But I just don't like that because, you know, I teach kind of by concepts, and why would you apply conservation of energy if the energy is not conserved? That's a little bit inconsistent. So I like to start with a concept that shows it from the beginning that that's not what's happening, and that's the modified work energy theorem. I don't know why people don't teach that anymore. They used to have it in books, but now they don't much, maybe because it just takes ink. I don't know. I don't really know why they, but I loved it. I think that fits better for my sensibility and the way that my teaching style, and also the way that I organize physics in my mind. So let's write the name of it. I didn't write it down. So that is, I'm gonna have to erase this over here. So that basically that constitutes everything you need to know from this chapter. And so now we're just going to work through several problems and focus on technique for this kind of thing. So equation 25 is the modified work energy theorem. And they call it the modified work energy theorem, I guess, as opposed to the modified conservative energy theorem, conservation of energy theorem, because it kind of looks like work energy. It has that form. Because, you know, the work energy theorem is work, or now we can say work total, right, equals delta K. So there's a change in mechanical energy equaling some kind of work. Here you have a change in the total mechanical energy equaling the work done by only the non-conservative forces. So it has, yeah, that's why they, yeah. So your equation 25. 25 and 26. Now, let's come back and apply that to this problem that we just did, where we say that the coefficient of friction is mu k for the object sliding down the plane. So basically, we go back in here and say that we know several things. We know m, we know theta, we know delta x, and now we know mu k, I guess it would be mu k. So start with the modified work energy theorem and see if you can come up with, you know, the velocity that when it gets down to the bottom. Again, remember initial velocity is 0. Not equals 0. And then compare it to this equation right here analytically. And you should clearly be able to see what I think a couple of people guessed, Armand, a couple of people, that when you get down here, you should have less, the velocity should be less than it is for equation 17. And that should be clear from the analytical solution. So go for it. See if you can, I'll at least get you started. For 26, so you have change in mechanical energy, right? So that kind of backing out of it. So you have, starting with 26, E final, or E at position 2. So always final minus position, final minus initial. So 2 minus 1 equals the work done by the non-conservative force. But in this case, So let's take a look at this. Let me help with this a little bit. So you have to now look at forces a little bit now. You have to do that. That's why I suggested back then, it's always a good thing to do it, even if you're going to do energy principles. But we've done this before, right? We know we have the normal force, which is going like this. Actually, let's erase, maybe erase some of this to make it look so messy now. So yeah, we've got the normal force going straight up, and we've got gravity down, straight down. Now remember about gravity. Gravity straight down, right? Mg. So remember, the angle stuff, we've got a component of gravity that is acting down the plane. And that component is mg sine theta. So all that stuff is reviewed. We've done all that so many times. And then now down this side, we have mg cosine theta. Okay. Now, normal force is a non-conservative force because it's in contact with the thing. But it doesn't actually do work on the system. We showed that when we last chapter, because it's 90 degrees relative to the direction of motion. So even though it is a non-conservative force because it's a force of contact, it doesn't do any work. That's why we didn't have to worry about it before, right? So I don't need to consider that guy. Now the component of gravity that's along the y direction also doesn't do any work for the same reason. And I actually forgot to put the frictional force in. We have the frictional force in now. So what direction does that act? Well, it's always opposite the direction of motion. So if the motion is down the plane, the frictional force is going to be up the plane. So that's Fk. And that definitely does work because it's anti-parallel to the direction of motion. The angle then it would be 180 degrees, for that. So only two forces do work are mg sine theta and Fk. So mg sine theta is a conservative force. Fk is a non-conservative force. So without even calculating the work or anything yet, that tells me that I would not start with this equation, delta E equals 0, because that says that the total mechanical energy is conserved. And I can see that it's not going to be because I have a non-conservative force actually doing work. The last time we did this, when mu k was 0, I could use this because even though I had a non-conservative force, it wasn't doing work. So I want to emphasize the fact that we're not making this distinction that non-conservative forces are not acting on the system. They can be, but as long as they're not doing work, it's possible that mechanical energy can still be conserved. So that's a kind of a subtle distinction that you want to make sure you're aware of. So that's what I'm actually saying. So that said, in this case, this guy is doing, there is non-conservative force doing work. Now, we've done the problem before. We actually did this before where last chapter, where we could calculate the work done by both and whatever, blah, blah, right? But it's easier this time, I think, to do this guy because we don't have to worry about calculating the work. All we want to know is what is the mechanical energy here and what is it down here? And then what we have to do on the right side. And we can see that if we're starting with the modified work energy theorem, the only thing that's going to be on the right side is going to be the only non-conservative force that's actually doing work on the system is going to be gravity. So in that equation, I would put Fk dotted into dx, where dx is the distance down the plane. And that's the setup that I need to work out. So I'm going to let you go from there, see how far you can get. Now on the right side, you just deal with kinetic energy and potential energy. Now the two positions on the left side. On the right side, we've done integrals like that before. You take the dot product first, and then you go through and work through the integral, right? And you have to figure out what fk is, put that in, you know, frictional force, and then work through the integral. And then in the end, you should have an unknown, with the unknown you're looking for should pop up somewhere in the equation, v2, and then you solve for that, and that's how and that will finish out the problem. So go ahead and take a couple minutes. I'm gonna give you a couple of minutes to see if you can work on that and knock that out. In fact, it's right about break time. So let's go ahead and have a working break. It's 1:25 or 2:25, and you break at 2:30. So let's take a 20-minute break where part of that is a working break. And so we'll come back about 20 quarter till, or maybe, you know, somewhere around there. Now, I hope you can see with this camera, because I need to use my phone on this break. So hope you can still see the board there. And can you see with camera 2, the computer camera here? That's where my hand is there. Can you see the board all right? Anybody?
I mean, it's
We can see
I.
it. Sorry.
You just need enough to write it down so you can continue.
All right. I can see. I don't know about other people, but I can make out what it says.
So yes, shall we? So let's go for, anybody get a solution? Can you hear me? Does my sound good?
We can hear. Sorry.
Okay, good. Yeah, so did anyone get a solution? Was able to compare it to that? How far did you get, Armand?
I took a break, but unfortunately halfway through I had to take a phone call from work. In the last 20 minutes, I was just getting reprimanded. So unfortunately, I couldn't come back and finish it.
Oh, I hope everything's okay.
Yeah, it's fine. More of just my boss just gets angry because it's a customer problem and he vented it out to me.
Okay. All right. Well, okay. Well, hang in there with that. Yeah. Anybody else? Yeah. No, okay, let's let me do it for you. Go ahead and get it out of the way. It's out. Oh, by the way, just a reminder, there's an election coming up on Wednesday, so remember to vote. People voting by mail now, so just remember your civic duty. Anyway, let's get back to this. So we've got stuff there. So what do we have? I'm gonna leave the solution right here if I can. I would rather leave the picture. Yeah, okay, so. So that's the previous solution. Now, so the right side is still kind of like what we did before. We don't really have to change that much, right? It's, you know, I just put in the parameters. So we have the left side, that is. So 28. So that's going to be, you know, basically K2 plus U2, and then minus quantity K1 plus U1 equals all the stuff on the right side, right? The integral fk dot dx. So we'll leave that for now. So on the left side, we've got some zeros that cancel out, that go out. At the top, it starts from rest, so the kinetic energy up there is 0. So that's 0 still, just like before. And down here, the potential energy is 0 when it gets to the bottom of H. So that's U2, 0. So we still have those terms over there, and this becomes basically K2 minus U1 equals the integral. Now, let's deal with the right side. The dot product is Fk dx times the cosine of the angle between dx and Fk. And again, dx down the plane, Fk up the plane. So the angle between them is 180 degrees. That makes sense because that's going to kick out a -1. And that is consistent with the fact that the work is negative because it's taking energy out of the system. So that goes to a -1, which when I write this now, I'll put that outside the integral. So then just so equals. So K2 minus U1 equals the integral. And basically I'm going from position 1 to position 2, x, and that becomes Fk, F sub k, and the minus sign is out there out front, dx. Now we need to put in what F2, okay, K2, U2, and Fk are. K2 is just kinetic energy 1/2 mv squared 2, so that becomes 1/2 mv sub 2 squared, then minus the potential energy up here, which is, so that's mg basically, and potential energy is potential energy. It's y, distance above the ground. Now I didn't actually give you the h, I gave you the delta x. So let's go ahead and, we still don't know what that value is, right? So just like in the last problem, we could write that h in terms of theta. So just to remind you of that, I'm going to put in mgh, and then say that's an unknown. So mg, I just like to do it that way, h, and then equals the integral, the minus the integral of Fk. Now what is Fk? Well, it's by definition uk times the normal force, dx. Okay. Now here, I'm going to just, so you have it in your notes, 32. So what did we say? We said that h is equal to delta x times the sine of theta. And then for the friction, we know that the normal force is equal to, I erased it right here, but from previous problems that we've done, we know it's equal to the vertical component of the weight. So this normal force here is equal to the mg sine theta here. Mg sine theta right there. So that becomes 33. So that's going to be normal force then is equal to mg, cosine, my bad, cosine theta. Cosine theta. Mg sine theta is the parallel component. Mg cos theta. And then we substitute that in. And we have, so substituting in 32, 33 into this guy, That then gives us that 1/2 mv2 squared minus mgh, but h is equal to delta x sine theta equals minus the integral of mu k mg cosine theta dx from basically x1 to x2 down the plane. Now, so if you evaluate this, like look at this, the unknowns, what do I know? I don't know V2. Everything here I know. And over here, basically everything I know with the exception of working out the integral. And also with the integral, all these things are constants. So they come outside of the integral, which is nice. So here I'm going to have 1/2 m v sub 2 squared minus mg delta x sine theta. All that's just a constant. We know all those values, so we could calculate that. So it equals minus mu k mg cosine theta. Now remember, theta is a constant because it's just the angle, the plane angle, doesn't change. So then I have the integral of x1 to x2 of just dx. And the only unknown in that guy is V2. So that's basically it. That's the end of step 6, and we just do the math and calculate. So let's do it. That integral just integrates to delta x. And I'm going to go ahead and I'm going to take this term over on the other side and then also do the integral. So then that becomes 1/2 mv squared. So that'll be equal to plus mg delta x sine theta. And then this is going to be a minus mu k mg cosine theta. And then that's times, basically that integrates to x from x1 to x2. As I said, that just becomes delta x. So that's 1/2 mv squared equals mg delta x sine theta minus mu k. I'm going to bring mu k times mg. I'm going to go ahead and put the delta x in front of the cosine. So delta x and then cosine of theta. Now the only unknown there is this guy. So now I solve for it. Well, I see right off m will cancel out at each term. So I can go ahead and do that. Out, out, out. I multiply through by 2 and then take the square root. So my final result is going to look something like this. V2 is equal to square root of 2g delta x sine theta minus mu k 2g delta x cosine theta all to the 1/2. I could actually simplify it a little bit further. I can factor out a 2g delta x. Let's do that. Well, actually, I could compare it right there because look at this. this velocity, the first time with friction, was equal to 2g delta x sine theta. Well, you can see that that's this term. And like we said, the total velocity for this strip should be smaller because we have friction. And sure enough, we're subtracting something from that term that has the coefficient of friction in it. So you can see that this is actually the friction term, the work done, and it's negative, so it's taking it out of the system. That's the energy done, well, it's not energy now, it's velocity, but that is a term associated with the energy that's taken out of the system. And this is associated with the energy that's putting, the term that's putting energy into the system, or at least converting potential energy into kinetic energy from the force of gravity. And it also makes sense that whenever there is no friction, when mu k goes to 0, that whole term goes to 0, and I get my solution back over here that I started with in the beginning. So that shows a symmetry of solutions, that the actual original solution is embedded in the new solution, and that it should reduce to the new solution under the circumstances that the frictional force goes to 0. So we could stop there, but I like a little better, I like to simplify a little better my tastes. So V sub 2 is equal to, I'm going to factor out the 2gx. So brackets 2g delta x. And then in parentheses, I'll have sine theta minus mu sub k cosine theta. Parentheses and then brackets again. So for my taste, that's a little bit clearer because I can definitely see that this is the first, the first term does give me this solution, but now I just see that the mu k cosine theta part is associated with the other guy over there. Okay, any questions about that? So that's how these problems work. That's how kind of work out. It keeps things organized for me. So what do you think about that? Any comments? David, what do you think of this? Questions? Are you there, David?
Yeah, sorry.
Yeah, what any questions about this? What do you think about this?
I think I just need to do a couple more practice problems on my own. But yeah, no, so far it looks I feel like I can understand it.
Theodore, how
Thanks
are
for
you?
checking in.
Yeah.
Professor called me.
Yeah, how do you think? How's this going? What do you feel about this? Questions or comments?
It's looks okay for me. I am gonna have to like look over it later though. Like just solidify myself some practice on it.
Yeah. Let's do a couple more. 11. Yeah, let's do one where let's put in a spring. Let's put in a spring. That would be an interesting problem, is using gravity and a spring together. You're going to see problems like that. Yeah. So I need to erase the board for this. So I want you to see if you can, does anyone finish writing? Give you a chance to copy. Give you a couple more minutes to get all that off the board. Up to equation 39. I'll leave that there for the time being, just in case you're still writing. I guess I have to, I guess just the last couple. Yeah. So what about something like this? Let's go back to the frictionless case and throw on a spring. And let's place the spring over here on a wall. Actually, let's do it like this. So now we're going to have two different surfaces, and for right now, both of the surfaces will be frictionless. So we're going to have surface 1 mu equals 0 and surface 2 mu equals 0. So basically, this is the frictionless problem, but I just want to distinguish two different surfaces. Actually, and we can make, let's do this. Let's make it a little longer, I guess. Bring that out over here. Okay. And we can also make this distance here delta x2. And of course, well, let's do it here. That distance is delta x2. And the distance down the plane is delta x1. So here on up. Delta x1, just like it was before. Okay, can you see the board all right? Is it dark enough? A little darker. All right. Now, again, we have a block, and so also this is angle theta, we know that. So we've got a block up here. Same thing, block up. It's going to start from rest and slip down the plane. But now this is what I want to know. That's block of mass m. So right now this is frictionless. Obviously, you know, we did the problem again, we can add in friction. But both of these surfaces right now are freaking, like say we could turn the friction on or off or something. So right now, I'm just distinguishing that they're two different surfaces, so not necessarily the same friction when they're turned on. So block one slides down the plane, it's going to pick up speed and then gets on this surface, but it's frictionless too, so it just continues moving, and then it compresses the spring a certain amount. And I want to know, given, so the only thing that so what do we know? We know theta, we know delta x1 and delta x2 and k. So what I want to know is how much will the spring be depressed when the mass hits that spring? It's going to hit it and depress it a little bit. So I'll put it in, you know, maybe depress it like that. So maybe this distance right here is some I don't know what that is. So we'll call that distance maybe d. So the spring will be compressed a certain distance d and then come to rest. Of course, the spring will push it back out, but we're going to end the problem where the thing slips down, hits the spring and depresses it and then stops. And how far is it? So I'll write the problem up. A mass starts, and we don't even know h. We still don't know h. We just know delta x. So what's given is m delta x1 delta x2 theta, the mu's, all the mu's are 0, mu1 equals mu2 equals 0, and the spring constant k. Those are the things that's given. And what we want to know is find what is d, the depression of the spring. So this is a case where we have two different potential energies. We have one associated with gravity and then one over here associated with the spring. Now, if we work this problem out, with Newton's laws and even work energy, now you might, it would be, it's not necessarily difficult, it's just a lot of moving parts. But the nice thing about this is that we really only need to look at certain points. And so the question is, if M starts from rest, on the ramp and slips down and hits the spring, how far is, how much does it compress the spring? Something like that. If M starts from rest, slips down the plane, into the spring, how far is the spring compressed? So again, the nice thing about conservation of energy is that you just need to look at critical points. We're familiar with this kind of, I've set that up for you already. Like, so position 1 and position 2, maximal potential energy down to, that energy being transformed to motion, and I guess kinetic if you note, and potential, but in this case, potential would be 0, gravitational potential, because you're at the bottom of the hill. And you could make your 0 potential mark there. So positions 1, that's critical. Then I guess position 2. Now here, since there's no friction there, you can kind of see that basically the energy is not going to change. If there were friction here, coefficient of friction, it would take energy out of the system. So whatever velocity it has here would be different here. And this is kind of implicit information, but since this is 0, it's just going to slide along at the same constant speed and then hit the spring. So that seems to be kind of it's an ideal spring, so we don't really have to worry about momentum or anything. The spring doesn't have any mass; it just has K. So that maybe is a critical point. I guess we could say that. So I'll put that 3. And then 4 is going to be the final position of the spring when it stops. So I guess I could. So 4. So that's what kind of stands out to me. I'm not even sure we really need 3. We'll show that in a moment why, but for now, let's just assume we do. And so, yeah, the spring constant is K, and I can that's K. Well, I think the most straightforward, really the most straightforward way to approach the problem is just look at the 2 endpoints. That's what I would do, I guess. You don't have to piecemeal. You can just go, I'm asking you, and again, that's the power of conservation of energy. It doesn't really matter it matters what happens in between, but in terms of forces and work and energy and that sort of thing, you can take it into consideration. Like you just really need to know what the difference in the mechanical energy is between those 2 points, to be honest with you. Yeah, I'm gonna go from there. But I still like to kind of look at certain critical areas, the things, because it doesn't matter. It's not going to hurt it to identify those things. But so let's just start with that. So can I use conservation of energy? Yeah, and not the work energy there. Why? Because as the block slides down the plane here, there's no friction doing work, so I don't have to worry about that. So it's just gravity doing work. The gravity is conservative. It comes through here, there's no friction there, so I don't have to worry about any work done. And so then I come over here, I hit that guy, and then I compress it. Well, the spring is a conservative force. So that's, I only have to worry about, so I know that all the energy I put in it when I place it up on this ramp is going to be in it when it gets to position 4. It'll still be there. It just have changed forms in different ways. So let's just do. So I start with conservation of energy then. Position 1, energy at position 1 equals the energy at position 4. And I guess that's the advantage of what I was trying to say, is that you don't really need to worry about all the different transformations in between. You just need to worry about the position where you start and the position where you end, and calculate and make sure that you know all the changes in potential energy between those and mechanical energy between those points. That's the advantage of conservation of energy versus even work energy theorem or something like that. And it just works out. So at position 1, I have mechanical energy. I have K1 plus U1, and then our mechanical energy is K4 plus U4. Okay. Now let's evaluate the zeros. If I'm starting from rest right here, then I don't have any kinetic energy. And if I end at rest here, I don't have any kinetic energy. I know this seems crazy because this could be you could do it a much more complicated way. And it would take a lot of more work if we did some of those other things like force and work energy. With conservation of energy, it's beautiful. So just very elegant, because it doesn't matter what happens in between here, how the work is transforming, the different things and all that. I know I got kinetic energy and that we just calculated it, right? And just imagine, like, you make the problem more complicated. Well, I'll just leave it at that. But you don't have to worry about that. It should all it should all work out. I have like conservation of energy between positions 1 and 2. I can do that. I just did it. Then between 2 and 3, there's no change. But then between 3 and 4, because it has kinetic energy here when it hits this thing, but I don't have to do any of that. All I need to do is the endpoints, and then it's going to work out. So let's just do. At the top there, again, I have MGH. Oh. So 1, 2, 3. And MG. And by now, I think we could see that the H is going to be delta X sine theta, but let's just go and put that step in. And over here, I have the potential energy associated with the compressed spring. Someone remind me, what is that formula? Dominic, do you remember the formula? We derived it last week or maybe Monday. I don't know.
Sorry, I couldn't make it Monday. I was cleaning house.
Okay, no worries. Armand, remember?
I'm sorry, can we see the question? I'm just bouncing in and out from the internet right now.
Oh, okay. It's
my Wi-Fi is kind of cutting out. Sorry.
Okay, the potential energy function for the spring. Anyone? Malachi, do you remember that last week? Or I don't know if you were. I think you were here. Yeah. Anyone? We derived it for the spring. In fact, where's Daniel? Oh, Daniel had to leave? Oh, there's no Daniel.
I think I have it.
Okay, what is it?
Is it 1/2 times kx squared?
Awesome. Yes. It's 1/2 kx squared. So that's what we have here. So 1/2 k, which we know, times, and the x, this is actually the d. The x is the amount of compression. So I'm just going to call that d. So 1/2 d squared. That's it. Now, there's two unknowns in that. One is H and one is D. So we need another equation. And just like before, you see the symmetry repeating in the different problems. That symmetry, this is H right here, this distance here. So that's just delta X sine theta. We've already done that, so we know what that is. I'll put that in, and bam, that's it. That's it. That's the end of step 6. So mg delta x sine theta is equal to 1/2 k d squared. And we just solve for d. We solve for d. Yeah. So I'm going to do that, and then I'm going to modify the problem in a different way. Like put friction in one of the surfaces or whatever. So let's solve it. Just solve for d. So we're going to have d is equal to, so the 2 goes over and divide through by the k and then take the square root. So we're going to have 2mg delta x sine theta over k, and the square root of all of that is how much the spring depresses. Isn't that something? And you don't really have to work out what's happening in between all that stuff. It's just the final and initial positions. Now, what I'm going to do now is change the problem and give mu2 some non-zero value. mu2 along delta x2. Now we'll do the problem again. How much is the spring going to be depressed? Well, we clearly, whatever the velocity is that it has when it gets here, it's going to change when it gets here. Okay. And so because energy is going to come out of the system. So because it's going slower at position 3, it's going to be depressed more. Now, the way the book is teaching you, this part would be the same if there's no friction. But if there is friction, then I believe what you have to do is you have to go through and calculate, like kind of piecemeal it to some degree. Maybe not. You can still do the work there, but I don't know. It's just, I don't even want to talk about it because it's just the way that I approach it is, again, look at what forces are on the object. I didn't draw them in because we've done this so much that we know that, again, with normal force here, gravity, all that stuff. And then the spring force, when it's depressed in, the Hooke's law force going back, we know those forces are there. And now friction going to be along this surface, all of that. But still, like, you don't necessarily have to draw that in, and if you understand them when you're doing conservation of energy, because energy, they're all scalar quantities. So the forces are in there, sure, particularly when you do the work energy, when you do the modified work energy theorem. But initially, if I'm approaching from energy, it's just a different kind of perspective that you can have if you're going to try that. So the point is that when I look at it, I know, again, here conservative forces acting from point 1 to point 2, non-conservative forces acting here, and then conservative forces acting again from point 3 to point 4. So energy is not going to be conserved, mechanical energy. So I don't start with this. I start with the modified work energy theorem. I do that that would be done in steps 3 and basically step 4 of the problem solving technique. So when I get to step 5, I'm not even trying to, I already am ahead of the game in that regard. So, and what did I teach you it was? Well, it's this. It's not that delta E is equal to 0, like it was over here. delta E is going to be equal to the work done by the non-conservative forces. Integral of F non dot dx or dy or whatever. Now, you can go in and draw it if you want, if you need to draw it here, but we know like when the block is here and it's moving along that surface, you can put those in. So when it's in this region here, it's going to have three forces on it. It's going to have a normal force up, right? It's going to have mg down. That's important to see that because the frictional force there is a little different because of we'll see in a minute, mg down, and then the frictional force in the opposite direction, right? Frictional force like this. But I've given you a lot of drill, right? Fk. So you know that F is going to be equal to mu2 times N, but you can easily see here that N is actually equal to mg in this particular, right? Because it's flat. If it were on the surface, just like in the last problem, N would be equal to mg cosine theta. So because we've done a lot of drill, those things, hopefully they'll start to pop out at you, right? Like it should be kind of somewhat in your mind memory now. But you still need to go through the steps. You're not memorizing problems or anything. You're going through and evaluating every time. So when we get to evaluating the right side of this equation, that's in there. Now, let me just point it out to you because we're not going to be able to do this problem. What if I had given both terms over here, right? Well, then you got two forces. So like when I write this out, like in this next step for the problem we are doing, for example, guess I should have started there, but I'll go ahead and start here. So 6. So then this next step is going to basically be, E1 to E4, E4 to E1. So I should have went the other way around this, but whatever. So E4 minus E1, and over here it's just, well, this integral, we know it's going to be constant. The minus sign is going to come out because they're 180 degrees. And then, I just had that one for us. I'm just going to write it. It's just going to be F, I'll call it F2 or minus F2 dx. Because we know friction is always going to be minus because it's opposite direction of motion. F2, basically delta x, where delta x is delta x2. I can just go ahead and do that integral right out. I don't have to do, I wanted to do it very explicitly the last time so that you see where it comes from. But basically, I don't even have to start with this formula. I could start with the fact that it's a constant force. But I personally just like to write the integral there to remind myself all the time. But I could have just went, F2 dot delta x. Anyway, F minus F2 delta x. What I'm trying to say is that if I had put this friction in here, then it's basically two integrals. One would be like F2, the one I'm doing from position 2 to position 3. And then the other is plus integral F or friction, F1 dot dx, where that goes from position 1 to position 2. The point is that when you set it up with this formula, the right side will always be the mechanical energy side, the left side that is. The right side is going to always be every term for any non-conservative force that's in the problem. So it's just clean. You don't have to worry about minus signs, where they go, because the minus signs will just work out whatever when you do it, right? So that's much more straightforward than the way I think your book is going to tell you. That will always be the case. But this is still 0 here, so we don't have a frictional force, so I don't need that term. I don't need that term. And this is the problem that I have to solve. E4 minus E1 is equal to the work done by the frictional force. Now it's just going to be F delta. It's going to be straightforward, right? F is going to be equal to mu2 mg, and then you solve, right? And this is delta x2, by the way. That's the given. So see if you can finish that and see what, and you know that the D should be smaller, right? Like it should compress it less distance than this problem. So again, we should be able to look at our final solution and see the initial solution embedded in there somehow. And it should be associated somehow with the frictional force, the coefficient of friction of this distance here, just like in the last problem. Does everybody see that? That makes sense? Theodore, talk to me.
So
Hello?
about first, did you say something? Did
What's
you
that?
mention my name? Did you mention my name? Sorry, I'm distracted at the moment. Something at home.
I did, yeah. I was asking, did you understand what I'm saying here?
For the past couple of minutes, I have not, unfortunately. There's something going on at home that has my attention.
Gotcha. All right, no worries. What about you, Malachi? You there? Hello? Okay. Yashwant, are you there? And whose iPhone? Who is that? Hello, iPhone? Okay. David, are you there?
Yeah.
Yeah, so give me some feedback on this. Does it make sense what I was just saying to you? Do you know how to proceed from equation 7?
See, it's just for me, it's the same thing, like it's similar to what I said last time. My bad, I'm rubbing my eyes right now. My eyes burn. I think I just need more practice with it. Just like most things, or for me personally, it always just comes down to just repetition and just trying to wrap my head around it in general. So yeah.
Yeah, but do you understand? So is there some question you have, like something you don't understand that you can specifically ask?
No, I think I understand. Yeah. Hold on. Sorry, my dog's barking at something. I'll be back. Sorry.
Okay, all right. Armand, how are you?
So far so good. It's just been, this is a long sort of class. I sort of have a tendency of drowsing out halfway through. But if I go back to the lesson again later on with the recording, I'll digest it a bit better.
Okay. Well, I do want to give you a little time to try to see if you can get a solution on that. How much time we got? Yeah, we got 45 minutes. So I'm going to give you a few minutes to see if you can make progress starting from here to get a solution and then compare it to equation 5. So again, this is a situation where we've, now, well, I'll put it here. Here, use that space. So that's the solution. And then now, give mu2 a value, a non-zero value. And calculate D again. It should be less. Okay. We don't need this over here anymore. All right. Let you focus on that a little bit. Okay, let's go ahead and try to knock this problem out because I'd like to do one more, which is a problem in your book that I do a lot with this section. But these problems I just thought were pretty interesting, and we'll do these. So let's do I mean, we could put in some numbers too. Let's put in like, let's say you have a spring constant of let's just do that real quick, just to give you an idea. So a spring, so mass of 5 kilograms. So let's say that M before we do this. So let's say, just to calculate the number here, so we can get a different number. So mass is equal to 5.00 kilograms. Let's say that theta is equal to 30.0 degrees. We can have delta x, 1 be, let's say 3.5 meters. And delta x2, let's just let that be like 0.25 meters, like 25 centimeters. And let's let mu 2 be 0.275. And let's let the spring constant K be, think like 400, is it 4,000? I think that's like a reasonable spring constant. 400, yeah, 4,000, between 300 and 4,000, 3,000 and 4,000, I think is like, so if you like look at any problem, let's do like, yeah, so here you go, spring constant K, did it give one? Oh, they're asking you to calculate the spring constant. So, most of these will tell you what the spring constant is. So 170 Newton per meter is one. Let's see. So the examples in the book. But like spring constant is usually a bit larger than that. Yeah. Okay, yes. All right, so I'm sorry, between 300 and 500. So let's do something like 350. Spring constant of 350 Newton per meter. So if we just put those numbers into our problem there, we can quickly calculate the value of the spring, of the displacement. So we have 2 times, so 5 kilograms, and 9.81 delta x, so that's delta x 1 actually. So you see, since there's no friction on that surface, the delta x2 isn't even a function of that thing. So what was that? Delta x1 was 3.5 meters. Actually, it's really not a function of delta x1. It's a function of h, which is delta x1 times sine theta, or whatever. And then theta is 30 degrees. Sine. And then k is 350. Okay, 350 divided by, and then take the square root. So it doesn't depress it that much. It depresses it 0.7 meters, so 7 centimeters. So that's reasonable. That's about what I would expect with the numbers I chose. So D is 0.7. So 0.7, that's in meters, because everything was in meters. And yeah, so for the first problem, so this is the solution, the answer would have been 7.7 meters. So that's, wait a minute, 0.7 meters, that's 70 centimeters. 0.7 meters. 70 centimeters. Okay, so it's a large spring. Okay. So 5A, 5B, D is equal to 70 centimeters. All right. Yeah, because the spring constant, I thought they usually are a factor of 10. Yeah, those are light springs. So let's make the spring. I'm kind of used to spring constants being a little bit more than that. So 4,000 would give it another order of magnitude. So let's make it more like 3,500. So 3,500. That's what it is. Yeah. Okay. So it doesn't matter. This is perfectly fine. I'm just trying to make it so much more realistic. Because 7 centimeters, that's kind of a long spring, but it could be. You don't know what the situation is, but you could see with another order of magnitude, that's going to make this 7 centimeters, which is more like what I was trying to go for. So 5B. So my first instinct was right. D is 7, approximately 7 centimeters. So yeah. So just let me do that again to make sure that I'm thinking of that right. Correct. Actually, yeah. So one more time. So 2 enter 3.5, 9.81. No. What? 2 enter 5 times 9, 3.5, 30 times, then K, 3,500, and then take the square root. Okay. Yeah, because it's squared, it doesn't cut it in half. My bad. It's just not gonna. I do like that a little bit better. So with the spring constant of 3,500, it brings it to 22 centimeters. Yeah. Oh, okay, sure. We'll leave it at 3,500, sure. So that brings it to 22 centimeters. All right, let's just go ahead and do the other one. So it should be less than 22 centimeters now because I'm taking energy out of the system. So let's see what we get. Yeah, we've got plenty of time. All right, over here, I'm gonna go a little bit fast because basic is the same. This is not gonna change over here. The left side doesn't change because, I have 0 kinetic energy up here. So that's gonna be MGH for position 1, and down here, no potential energy right before it hits this surface. So, because it's at 0, and the kinetic energy is going to be a maximum, and then it starts to lose energy as it goes through. So here we're going to still have, I'll write out the steps. So it would be 1/2 mv squared down there minus mgh, which is delta x, mg delta x sine theta for E1. Well, let's just skip a step. So mgh equals, and over here, minus mu 2 mg delta x2. Well, actually, let's do this. Let's just so you have it in your notes. So mu n delta x2. And then I'll put in the ancillary issues that here h is equal to delta x sine theta, and that's from the geometry. This guy, remind you, delta x, theta, and h. And for this equation, the normal force is equal to mg, and that's because of that's from the first law, that force equals 0 in region 2. So that becomes normal force minus mg equals 0. So we stick those into these guys, and we have now 1/2 mv. And I guess, yeah, this is still mv2, so we have to distinguish. So squared v2 minus mg delta x1 sine theta, and then equals minus mu2 mg delta x2. Well, I said it doesn't change, but it's kind of a different problem, so forgive me for that. But yeah, it doesn't really change, but the way we set it up changed a little bit. So you see that term is in there, but now I have the velocity term over on the other side there now. And yeah, because I didn't have, yeah, my bad. I was comparing it to the problem before because we just went from here to here. We didn't go from here to here, my bad. So, oh, wait a minute, what am I doing? What am I saying? You know what, I've messed you guys up. That's not what I don't need to, I don't, my bad. This is not, this is wrong. This is, yeah, I got mixed up. This is from position 1 to position 2. We're going from position 1 to position 4. So my bad. I'm so sorry. Golly. I've kind of reverted to the problem we did before we did this one somehow out in my mind. I know I'm getting tired. I think I'm hungry. Let's just start over from here. From here. Sorry. Position 1 to position 4. And the thing I told you is that you don't have to worry about basically what I was doing is working all that stuff in here. You don't really have to do that. But you do know that you kind of have to take a little bit in consideration because you realize between those two steps, there's this non-conservative work done. But that's not handled on this side. That's handled over here. So that work right there, it doesn't matter where it happens. You're handling over here. Another advantage of having it is setting it up like this. And this stuff is still the same, but between these 2 points. So that's all we have to worry about. So in that regard, this actually won't, well, it's a slightly different issue. So let's go ahead and look at it again. So between this position, we have basically just potential energy here and potential energy at that point, position 4. So position 4, it's going to be the 1/2 K, basically now the new D, whatever, squared, minus MGH up at this point, MGH, which is equal to delta X sine theta. Equals the minus mu2 in delta X2. In fact, let's do it like this. Let's make this H, where H is this value, and then equals minus mu2 in delta X2. Sorry about that. So again, we can put in those issues that H is equal to delta X1 sine theta, okay? And N is equal to mg, all right, by the second law. So when we stick those in, now we have 1/2 K D squared minus mg delta X sine theta, and then minus mu to mg delta X2. There you go. And the only unknown in all of that actually equals equals third time's a charm, equals minus mu2 mg delta X2. Now the only unknown in this equation is this guy. So we just solve for it. And when we do, I'll do it in steps. I'll take this guy over. So we have first, so we have 12. So 1/2 K D equals mg delta X sine theta, and minus mu2 mg delta X2, multiplying through the basically 2 over K, and that's squared. So D is equal to, I have to take the square root, so be 2 mg delta X sine theta minus 2 mu2 mg delta X2, all of that over K to the square root. And now I can factor out some things. And my final result Well, actually, I can already see that it's consistent with what we said, because this first term here, 2mg delta x sine theta over k, that's this guy. And then I'm subtracting something from that. So definitely this new distance with friction is going to be smaller than the first one. And maybe I should distinguish so you have in your notes, this is like d mu or something where I'm have friction on it or whatever. But well, I don't know, I don't like that, but yeah. So yeah, it's definitely going to be smaller. And I like to simplify when I can. So again, we can say that D, final D is equal to, I'm gonna factor out the 2mg delta x. Well, I can't, I just have to factor out the 2mg. Yeah, so 2mg, and I'm gonna go ahead and put that over k out here. And that's gonna be multiplied by, in the brackets, I'll have delta x1 sine of 30 degrees minus mu2, and there's no, yeah, minus mu2 delta x2 in parentheses and brackets to the 1/2. So the thing I'm subtracting is associated with, it's a term associated with the friction, and mu2 times delta x2 along that distance. And that makes sense. That makes sense that that should be what would decrease the displacement. So that's the solution that we compare over here. And when we put in the numbers, it should be something less than 22 centimeters, which it will be. Still something reasonable. So let's go ahead and put those numbers in. And see what the actual value is. Oh. So we're going to have 2 times 5 kilograms times 9.81 divided by K, which is 3,500. And multiplied by delta X1, which was 3.5 centimeters times sine of 30. But then minus that other thing, which is mu2, just 0.275. And delta x2 is 0.25 meters. And it doesn't subtract a whole lot, does it? Should have made it longer, or maybe the coefficient larger. And then multiplied by this thing. And then take the square root. Yeah, so rounded off is about the same. You know what? I'm going to, it's actually it is different, 0.217, but that rounds off to 0.22. I'm gonna make, let's just see how much that'll change. I'm gonna make this more like 0.35. Because it doesn't affect this at all, because it wasn't, you know, X2 or mu2 wasn't in there. So I could do a couple of things. It's only 25 centimeters. That's only that much. I was wondering, let's make this like 1.5 meters, the distance of X2. 1.5 meters. Actually, let's change one thing at a time. So yeah, let's just make that 1.5 meters. Maybe that's better. Now, if I do that, and then do the problem again, I'm going to just do the solution again. So I didn't save that. So can I back out? No, I can't. So 2, enter 3,500. Can you imagine if I had left it at 350K, it would have been even less. So then delta x, which was 1, which is 5 into 30. Yeah, and then over here now I have 1.5 times 0.275. That's a little better than minus. I think we'll get a difference this time, times the square root. Yeah, that's better. So that turns out to be 19 centimeters. That's a little bit more obvious. I like that a little better. Yeah, so you see it definitely makes a difference. This is a good problem. It's a pretty good design. So D is about, it takes a little bit of energy out and it depresses it about 2 centimeters less than before, 2 or 3. So 19 points, and rounds to, 19.4 centimeters. Take 3 significant digits. So D, in this case, D would be equal to approximately 19.4 centimeters. With those numbers, 1.5 as the distance. All right, so yeah, just start working through some of those problems. And I would, again, go to the back of the book and work some of those examples. I think those are pretty good examples back there in the chapter. Got plenty of them there to work through. Okay. Mm-hmm. Mm-hmm.
Real quick, I may not be seeing this exactly right, but at the
Mhm.
bottom, very last equation for D, did you already put in the value for theta?
Yeah, I should have just kept it theta, but yeah, I just put in the value. I don't know why I did that, but that's just theta. So you can compare it back to the other solution.
Oh,
In
okay.
this case, theta was 30 degrees. So I'll take it out and just leave it as theta. You're right. That's clearly.
Yeah, that was throwing me for a loop for a second.
Sorry about that. Yeah, so you could easily compare it back to the original solution. That was just a brain fart. I don't know. I had 30 in my mind when I wrote through that, and I just kept it. Oh. This would be a much more, again, not difficult, but a much more kind of tedious problem if you had to do it with accounting for the forces. And I think I showed you that at least in the last chapter where you could do something with work, and then you could do it with kinematics and Newton's laws. Work energy, that is. But work energy is even a little bit more cumbersome than conservation of energy, basically. So, it seems like this might be a lot of, because I don't skip any steps when I go through because I want to be transparent. So don't let that overwhelm you. Basically, most of what I'm working out here is actually step 7. Like basically from equation 6 on is essentially like step 7, not step 6 in the problem solving technique. So, with conservation of energy, really you go through those first 6 steps pretty quickly. And that's where, you know, where so with the Newton's law route, basically step 7 would still be just as cumbersome, but you'd have a lot more work to do to get to step 6. You know, steps 1 through 6 with going with Newton's laws and kinematics, or with even with work energy, be a little bit more. So conservation of energy really is pretty brilliant approach to analyzing systems and problems. But I still, you know, think it's, well, it's not necessary, but it's nice to have the foundation of Newton's laws, establishing, approaching it from a certain point of view. And I definitely would encourage, though, if you know, if from a studying technique, you know, go back and do these kinds of problems with force and kinematics or work energy, so that you can fully appreciate the difference. Honestly, that's what I did, you know, to just convince myself what was the difference, what are the subtle differences, and why we have to. So it helps to do that, because it just helps. So I would encourage you to do that if you're so inclined and motivated, because you definitely will learn some things, the subtleties of the differences there. Okay. So what time we got? Oh, that's it. It's 4:32. So any other questions, problems, troubles, or gripes? This is chapter 8. So we got to keep moving it along, I think. Yeah. I might do 1 or 2 other problems on Monday morning, and I'll open up the chat. I think it's open already. Let you, or maybe it's not. So I'll open up chapter 8 and let you start working through that. But we got to move on to chapter 9 with collision, center of mass, and yeah. I guess also moment of inertia is in that chapter. Those are 3 big things. Moment of inertia, center of mass, and yeah, moment of inertia, center of mass, and collisions. Wait, is that in there? No, I'm confused. I think it's just, what is chapter 7? Let's take a look at your book real quick. Then I'll let you go. Just get in my mind. So most, yeah. So chapter 9, linear momentum. So that's collisions, and so center of mass and collisions, momentum with collisions, momentum, okay. There's your collisions, lots of collisions. So no, I'm bad. No moment of inertia. So there's collisions. So there's a lot to cover there, but it's nice stuff. We're going to do conservation of energy. So we get the other conservation theorem, conservation of momentum, and define momentum, which we did earlier, but I told you I'd come back to it. And yeah, and then collisions, some derivations that we go through. So we're kicking it. But yeah. All right, cool. So questions, problems, troubles, and or gripos. All right. I guess class dismissed. And